We have visualized the convolution process. Now let us see a quicker method of determining the output sequences, and that can be done with the help of generator polynomials. So we have here the generator sequences G1 100, G2 011 and G3 110. The polynomials corresponding to these generator sequences would be, this one would be 1. For G2 it would be, since we have a 0 at this location and 2 1s over here, so this is for 0 delay, hence 0 into d to the power 0 plus 1 delay, 1 into d to the power of 1, which is this term, and this has 2 delays, so 1 into d square, which is this term. And for G3 110, by similar reasoning, G3d is going to be 1 1, and since there is a 0 over here, so no term corresponding to d square. And this was the message sequence that we had taken as an example. So the corresponding polynomial representation of this message sequence would be 1 plus d plus, there is no term of d square, so it won't be here. Then the term corresponding to coefficient corresponding to d cube is also 0, so we don't write d cube over here, and the coefficient corresponding to d to the power 4 is 1, so we write d to the power 4 over here. Now to obtain the first output sequence, that is y1d in its polynomial form, we simply multiply g1d by ud. So g1d was 1 over here, and this was the message sequence, so 1 into 1 plus d to the power 4, that is 1 plus d to the power 4. And now we can get back the bit value from this polynomial representation. So 1, then we have d, so another 1. There are no terms corresponding to d square and d cube, so we write 0 over here. There is this term corresponding to d to the power 4, and we write a 1 over here. Next, for determining y2d, we just take the product of g2d and the message sequence ud. So d plus d square into 1 plus d to the power 4. I have simply multiplied this and simplified to get d plus d cube plus d to the power 5 plus d to the power 6. Once again, remember we are doing modulo 2 operations over here, so d square and d square, these two terms get cancelled. And finally, from this polynomial representation we get the corresponding bit sequence for y2 as, there is no 1 over here, so I write a 0 first, then I have d, so 1 over here, no d square term, so 0, d cube, no d to the power 4 term, so again a 0, then d to the power 5 and d to the power 6. Finally, for y3d, I simply multiply g3d by ud and I get this polynomial representation, and the bit representation corresponding to this would be 1. There is no term corresponding to d, so I write a 0 over here. I have d square, so I write a 1 over here. The coefficient of d cube over here is 0, so I write 0. Coefficient of d to the power 4 is 1. Coefficient of d to the power 5 is 1. Now I already have the 3 output sequences. Now this is the longest output sequence, it has 7 bits. This initially had 5 bits and this initially had 6 bits. So in order to make all the sequences of equal length, I have added 2 more zeros over here and I have added 1 0 over here, and finally I get the output sequences. I take y1, y2 and y3 and write over here 1 0 1. At the next time instant I take the value of 1, which is this, then y2, which is this, and again y3 0, which is this. So this is how I form the complete output sequence.